Pluto, the enigmatic dwarf planet situated at the far reaches of our solar system, is generating enthusiasm within the astronomical community. Recent findings suggest a potential encounter with Neptune, which is causing concern among scientists and space enthusiasts alike. Renowned specialists, including Neil deGrasse Tyson and Maya Waku, have expressed concerns about the possible consequences of this cosmic event. But how did Pluto find itself on a collision trajectory with its distant companion? And what could this cosmic clash mean for us here on Earth? Let's investigate this developing circumstance. Once regarded as a full-fledged planet, Pluto was later redefined as a dwarf planet because of its unique orbit. Despite this classification shift, it continues to fascinate and engage astronomers. Recent forecasts from leading scientists highlight a disturbingly close proximity between Pluto's trajectory and that of Neptune. These experts warn of a possible accident between the two celestial bodies, posing a significant risk to Earth. Pluto's orbital characteristics around the Sun are unique within our solar system. Its revolution spans an extensive 248 years, and since its discovery in 1930, Pluto has not yet completed a full orbit. Adding to its allure, the highly elliptical nature of its orbit contrasts sharply with the nearly circular paths of the major planets. Moreover, Pluto's orbit is tilted at 17 to the ecliptic plane, resulting in a steeper trajectory compared to other planets. One remarkable feature of Pluto's orbit is its intersection with the path taken by Neptune for roughly 20 years during each orbit. Pluto travels closer to the Sun than Neptune, defying expectations based on their respective positions in the solar system. So why hasn't a collision occurred between Pluto and Neptune? The answer lies in the effects of gravity exerted by other planets. The investigation of Pluto's orbit began shortly after its discovery, revealing a puzzling trajectory for astronomers. Unlike most planets, whose orbits are relatively aligned with the ecliptic plane, Pluto exhibits distinctive characteristics, including a steep tilt and an elliptical shape. The mystery deepened with the understanding that Pluto's orbit intersects with Neptune's. The stability of Pluto's orbit amid these complexities provides proof of the intricate nature of celestial mechanics. The three-body problem in astronomy involves analyzing the motion and gravitational interactions among three celestial bodies, like Pluto, Neptune, and the Sun. This problem sheds light on the complex interplay of their trajectories and gravitational influences. Terms like asymptotic vibration, latitude vibration, and VZK oscillation aid in resolving this celestial enigma. Astrophysicists assert that the south vibration, which keeps planets in balance in their orbits, plays a crucial role regarding Pluto and Neptune. This term signifies that when Pluto crosses Neptune's orbit, it is positioned at least 90 away from Neptune, effectively preventing potential collisions. Latitude vibration ensures that when Pluto moves toward Neptune or another large planet, it remains significantly above their orbital plane, providing an added layer of protection against impacts. The VZK oscillation elucidates why Pluto's orbit around the Sun seems peculiar, yet remains smooth over time. Despite numerical apparent randomness in space, simulations from the late 1980s indicated that, while Pluto's orbit exhibits stable properties, it is technically chaotic, with minor initial variations leading to significant changes over millions of years. Nevertheless, Pluto's unique orbit maintains stability over incredibly long durations that control the chaos. Recent computer experiments have improved our comprehension of how larger planets like Neptune, Jupiter, and Saturn affect Pluto's path around the Sun, the unique relationship between Neptune and Pluto where, for every 3 orbits of Neptune, Pluto completes 2 greatly contributes to the stability of Pluto's orbit. Additionally, Jupiter's enormous gravity exerts considerable influence, while Saturn's impact, although smaller, also plays a part. Through extensive tests, scientists have shown that the combined effects of Neptune Jupiter, and Saturn ensure the secure and stable movement of Pluto. In space for billions of years, these phenomena are vital for maintaining the order and predictability of celestial movements in the universe. Without such interactions, the solar system would be susceptible to greater chaos and unpredictability, potentially leading to collisions or deviations from stable paths, causing ripple effects on other celestial entities. Understanding Pluto's orbit is particularly important amid discussions regarding a potential collision with Neptune in the future. This knowledge provides a clearer insight into the dynamic nature of the solar system. Pluto's situation underscores how orbits that appear to be unstable can achieve equilibrium through the intricate interaction between the forces of gravity and orbital mechanics. Continuous observation and study of these phenomena are essential for gaining a better understanding of our position in the universe. Exploring the vastness of space often reveals the unpredictable nature of celestial bodies, and the orbit of Pluto stands as a prime example of this unpredictability. The idea of orbital chaos vividly illustrates the sensitive dependence of a celestial object's path on its initial conditions, as depicted in Pluto's case. Even subtle variations in the dwarf planet's position or velocity can significantly alter its long-term trajectory. Computer simulations of this trajectory have proven crucial in aiding scientists to comprehend how Pluto moves through space. By making small adjustments in these simulations, astronomers can observe how minor modifications can greatly impact Pluto's path. In the late 1980s, simulations uncovered an intriguing facet of Pluto's trajectory. Despite features like latitude and asymptotic vibration that contributes to its stability, Pluto's orbit can still demonstrate unpredictability. Even a minuscule initial difference in Pluto's position or speed can result in substantial changes to its route over many years. Despite this inherent chaos, Pluto's orbit remains stable for an exceptionally long time, extending over billions of years. This suggests that beneath its seemingly erratic behavior, Pluto's journey around the Sun follows an organized order. Predicting cosmic events, particularly with planets like Pluto that possess unpredictable orbits, is quite difficult. The inherent unpredictability of these systems renders long-term forecasts uncertain. Numerical simulations assist us in understanding and anticipating the future paths of celestial bodies. But they also reveal the limitations of our predictive capabilities. These models heavily rely on precise initial conditions and simulate complex interactions. Even the smallest error can result in drastically different outcomes, making accurate predictions difficult. The erratic nature of space travel, as Pluto's orbit demonstrates, serves as a reminder of the ever-evolving universe. While we've made strides in understanding space, Pluto's case highlights our ongoing limited understanding. The gravitational effects of massive planets on Pluto's orbit offer important insights into the larger dynamics of the solar system. It demonstrates how the existence of each planet and its location can influence the stability and path of other celestial bodies within the system. Despite these complex interactions, leading astrophysicists are voicing concerns about a possible collision between Pluto and Neptune. This raises questions regarding the reason for the apparent unlikely event that has become significant. Neil deGrasse Tyson's concern, a notable astrophysicist, provides a distinctive viewpoint on the mysteries of our solar system, particularly concerning Pluto. Tyson, famous for redefining Pluto as a dwarf planet rather than a full planet, shares valuable insights into the ongoing evolution of our understanding of Pluto's mechanics from a celestial perspective. Reclassification, as opposed to a setback, is a vital adjustment reflecting our gaining a better understanding of the many objects orbiting the Sun. His perspective on celestial mechanics highlights the importance of continuous learning and adaptation. He sees the complexities of orbits like Pluto's as reminders of the vast unknowns that remain in space. Tyson believes that the public's fascination and astronomy's fascination with mysteries is captivating. And he also understands how events in space and new discoveries spark public interest in astronomy. He argues that events like Pluto's reclassification and its peculiar orbit present chances to engage the public's imagination and curiosity about the universe through talks about the dynamic and often counterintuitive aspects of celestial mechanics. Tyson seeks to foster a deeper understanding and appreciation of the cosmos. He opens up a chance for the general public to marvel at the wonders and enigmas of the universe, collaborating actively with other scientists. He alerts the public to the potential dangers of Pluto's unpredictable orbit. Following extensive research on Pluto, he has raised alarms about the three-body problem, suggesting that a collision with Neptune may be imminent. Furthermore, Tyson emphasizes how such an event could disrupt the equilibrium of the universe, potentially leading to catastrophic results that could even have an impact on Earth. A collision between Pluto and Neptune would be an extraordinary and calamitous occurrence in the solar system. The impact would release a significant amount of energy, likely shattering Pluto due to its smaller size and icy composition. Debris from the impact could scatter throughout the solar system, posing risks to the moons of other planets. For Neptune, such a collision could alter its orbit and atmosphere. Depending on the specific details of the incident, Michio Kaku, a well-known theoretical physicist recognized for his contributions to string theory and science communication, offers a unique perspective on this matter. His insights into the future of space exploration and the connection between celestial mechanics and theoretical physics provide profound knowledge of phenomena like Pluto's orbit. You've used the search for Pluto and its trajectory as a glimpse into the future of space exploration. According to Kaku, comprehending the intricate gravitational interactions and orbital dynamics of celestial bodies like Pluto can provide important information for the future. Space missions can benefit from this knowledge in successfully traversing the solar system, predicting potential hazards, and planning trips to faraway regions of our solar system and beyond. Kaku emphasizes that the lessons learned from Pluto's orbit can be applied to the exploration of other celestial bodies, establishing a framework for approaching and understanding far-off worlds. In discussions about planetary physics, Kaku frequently highlights the deep connection between celestial mechanics and theoretical physics. He believes that the movements and interactions of planets, such as the gravitational interplay between Pluto and Neptune, are not isolated phenomena, but are linked to fundamental physical principles. Kaku's work in theoretical physics, especially in string theory, aims to grasp these principles at their most foundational level. He recommends studying the intricacies of celestial mechanics, such as Pluto's orbit, to provide insights into the underlying laws of the universe. Like Tyson, Kaku has addressed the possibility of a collision, relating it to his theories about the cosmos. If Pluto and Neptune were to collide, it would mark a significant event in astrophysics, offering a rare observational opportunity that could deepen our understanding of string theory. String theory, which replaces point-like particles with one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. A collision of such a size in the solar system could create extreme conditions of energy and gravity, yielding insights into the behavior of fundamental particles and forces. Under such circumstances, a central focus in string theory. Moreover, the gravitational waves produced by the collision could provide valuable data for testing predictions of string theory related to gravity and spacetime. Even though the direct effects on Earth would be minimal due to our distance from the outer solar system, the scientific implications of such an event could be significant and potentially beneficial to our understanding of the fundamental nature of the universe, as characterized by string theory and other areas of theoretical physics. Pluto's orbit exemplifies the mechanics of the universe, demonstrating both stability and chaos within our solar system. The unique characteristics of its trajectory, shaped by the forces of gravity exerted by planets, particularly Neptune, emphasize the dynamic and intricate nature of the universe. Space is full of multiple enigmas, and the three-body problem is just one among them. Other potential disasters await scientific exploration, although the chances of planets colliding in space are exceedingly low. It remains a possibility. The way in which planetary orbits are influenced by various factors including gravitational interactions is illustrated by the three-body problem. In certain stellar systems such as TRAPPIST-1, which contains 7 Earth-sized planets, gravitational forces create rhythmic patterns known as orbital resonances. These patterns can, over time, destabilize the trajectories of planets, potentially leading to collisions. Despite the crowded nature of systems like TRAPPIST-1, collisions are not currently happening. Scientists are diligently monitoring these systems to comprehend how one planet affects another's path, particularly when in close proximity. This knowledge helps us grasp the movement of planets through space. Rogue planets, which wander through space without orbiting a star, introduce an additional unpredictable factor. These planets, once part of a star system, can be ejected as a result of gravitational disturbances or other cosmic events, such as the close passage of another star or instability in multiple systems. Over time, these wandering planets can travel vast distances, potentially reaching areas far removed from their origins. During their individual trips, there exists a chance they may intersect with other systems of stars. If one of these nomadic planets were to enter another solar system, there is a slight possibility of colliding with a planet within that system. However, given the vast and mostly empty expanse of space, the possibility of a rogue planet directly impacting another planet is extraordinarily low. And rogue planets, in comparison to stars and planets in stable orbits, are relatively uncommon, making such encounters even more improbable.